Hey folks, welcome back to the show. Today's guest is someone I've been looking forward to having on the show ever since I heard about his work creating a new open clinical data set from the University of Amsterdam Medical Center. From an engineering and data science perspective, this is the data that fuels our work. And from the clinical science perspective, this brings in a lot of really interesting questions from how do you actually create a data set, how do you select the data that you're going to be recording, which aspects of digital medicine really represent the clinical mechanisms at work. And then basically bring that together. How are you making sure that patients who are being recorded actually benefit from this data, and what are the ethical implications of that? So I have a really exciting guest today, Paul Elbers. Been looking forward to interviewing him for a while. If this type of work interests you, don't forget to subscribe, leave a like, leave a comment. And now we will do our quick little intro jingle, and then on to Paul Elbers.
Welcome to the Pod of Asclepius, your healthcare technology podcast for the technical crowd. We're bringing the technical experts of engineering, entrepreneurship, data science, and regulation straight to your earbuds. And here's your host, Glenn Wright-Colopy.
All right, great. So, Paul, welcome to the show. It's great to have you on. We always enjoy having clinicians on. Maybe you could tell us a little bit about yourself and your research.
Sure, Glenn. Thanks for having me. It's a great honor to be on your show. My name is Paul Elbers, and I am a clinical intensivist, so a medical specialist in the field of intensive care medicine at Amsterdam UMC, which is obviously in Amsterdam in the Netherlands. And besides being a clinician, I also lead a research group. It is called Right Data Right Now. And the specific purpose of this group is to bring data science, and more specifically predictive models, usually geared towards machine learning nowadays, to the bedside of critically ill patients. And that is, of course, for the benefit of the future health of these patients.
Great. And maybe just to warm everyone up, you could tell us about the database that you have created, because when I saw it at first, it seemed like something on par with PhysioNet and things like that. It reminded me of, it was clearly a huge undertaking. And maybe you could just tell us, what are all the components in this data set that you've created?
Sure. So AmsterdamUMCdb, as it is called, it is actually inspired by the work done by PhysioNet, and in particular their mimic database containing de-identified ICU data. So much like that, AmsterdamUMCdb also contains ICU data related to real intensive care patients having been treated at our ICU between the years 2003 and 2016. It is routinely collected data from these patients, and of course robustly de-identified. I guess we will come to speak in much greater detail about that later. But for now, it is, I think, important to understand that the main difference between our database and Mimic, I mean, there are many, but the most important ones is that it is more granular. So the data density is richer, and also the patients are obviously from Europe, and because intensive care medicine is structured differently between continents, these patients are generally sicker than those than in Mimic.
Yeah, that's really interesting. Actually, you've naturally led to the first question that I want to have, but just to clarify, one of the key differences in sort of clinical paradigms between U.S. hospitals, for example, and European and UK hospitals is the classification of sort of that intensive care unit and the step-down unit and things like that, where broadly speaking, in UK and European hospitals, the intensive care unit and those more critical wards have more acutely ill patients. And then patients who are less acutely ill are triaged into a more general, less acute ward. Whereas in the US, there's a bit more of mixing at the intensive care level, where the intensive care and the critical care patients are a much broader range of critical illness. So there's less acute patients in that. Is that how you describe it? What's a better way to say that, Paul?
No, so I think you describe it quite correctly. So I mean the sheer number of intensive care or critical care beds per capita is much larger in the States as compared to my country, the Netherlands. So this means that there is both a higher occupancy rate in general in critical care, but also that critical care is reserved predominantly for really sick people. So that is probably best reflected in the intubation rate of patients. So the patients on mechanical ventilation, which is very high in the Amsterdam database, whereas it is less in other databases such as Mimic.
Yeah, Paul, I have to admit, you're immediately just like the highlight reel of my clinical interests, bringing up respiratory, mechanically ventilated patients who are, I think, probably one of the most interesting set of patients, both from a data perspective and from a clinical science perspective, and really pushing the bounds of clinical science to its limit, in the sense that, you know, these are patients where there are certain aspects that are heavily controlled and they are heavily monitored, but there are so many confounding aspects that it's hard to really, you know, pinpoint down for a patient by patient that this is a patient who is essentially repeating the same process as another patient. But I wanted to, instead of talking about that, because, you know, that's a very deep rabbit hole to get down into, you're an intensivist, and I'm curious a bit, does this database reflect your clinical interest as an intensivist? So is this primarily a critical care and intensive care database, or are there also patients from the general ward?
So this data has been collected exclusively on the intensive care unit. So it mainly consists of a lot of data points, mostly related to monitoring devices, but also to life support devices, with a granularity of up to 1 data point per minute per parameter or feature, so you will. And so there are about just short of a billion data points in the data set. But again, as I briefly told you, it is ICU only. So although there will be some data from the trajectories of these patients just prior to the ICU, I would say the vast majority of data actually has been collected from their ICU stay. So to answer your question more directly, so it is exactly my clinical interest, these patients.
Great. And just to help clarify for data scientists, to put this a little bit more in data scientist parlance, I think one of the interesting things about this is that when we say that this is exclusively ICU patients, and he's collected all this data on ICU, very critical patients, maybe to the untrained ear that might sound like, oh, this is a very small subset of hospital patients. But I think what's important about this is that what Paul is saying is that he's collected a set of patients who typically are very sparse. So the data on them is very sparse from the perspective of when patients are critically ill, they can be critically ill in a great many ways. And so by focusing on this specific patient population, he's really helping try to sort of explore that the data space of the most acutely ill patients. So it's sort of like he's capturing the tail end data where we have the least data, which is also where we need the most clinical inference, and we need the most help with clinical inference. So to me, this is really exciting that you have essentially so densely sampled and densely monitored these patients who previously we have the least amount of data on. So you're sort of exploring a new part of a jungle, if you will, of the available clinical data. And so along that note, I'm just curious, could you just explain to us a little bit sort of what are the typical clinical scenarios of these patients involved? We mentioned mechanical ventilation, so patients who are unable to breathe for themselves. What are the other sort of typical clinical scenarios that these patients are in?
Yeah, so the variety of critically ill patients is quite large. of course, they all have in common that they are pretty sick, right? Otherwise, they would be called critically ill. And to reflect first a little bit on your previous comments, so it's important to understand that it is important to address their health and try to improve that by, for example, algorithms, because as the mortality is high, it has a direct benefit to these patients, but also the costs of intensive care per patient are very, very high. In Europe, it is estimated to cost about 3,000 euros, so about 3,500 US dollars a day, but that is many times more for US patients. So that is why I think this data is important. To go back to your question related to the different patient journeys you might expect in a typical ICU from Europe, this can vary, for example, from patients with respiratory failure, for example, suffering from severe pneumonia, to patients after a cardiac arrest, after which they would typically be treated in intensive care units and also being mechanically ventilated. To a large majority of patients having been diagnosed with sepsis, so bloodstream infection with microorganisms, which usually leads to multiple organ failure. So these patients are typically hooked up to a lot of machines, also the mechanical ventilator, but maybe also circulatory support with a intra-aortic balloon pump, or even a heart-lung machine, which is often called extracorporeal membrane oxygenation, or dialysis machines such as continuous hemofiltration. Monitors, of course. There's lab works that are up to 16 times a day. We have lab values for these persons, and there's of course imaging. So you name it, it will be in the data set. So they're very densely monitored because they're so acutely ill.
I think that what this highlights is that while all these patients are similar in the sense that they are very critically ill, they are all critically ill in very heterogeneous, very different ways. So a patient with sepsis, for example, while yes, they are effectively risking death and will have a high chance of mortality, the underlying mechanisms that will kill them are different from a patient, for example, who has cardiac arrest and things like that. There are, of course, comorbidities in that, but the idea is that these patients are only similar in the sense that they are at high risk of death. Physiologically, phenotypically, things like that, these patients diverge greatly. So I guess if a data scientist were to come in and start looking at this from a bird's eye view, is the data segmented into things like, okay, here is here's like a cardiac arrest ward, here is the neuro ward, here is the respiratory ward? Is that sort of the first high level view that people would take?
Yeah, Glenn, excellent comment. So first of all, when you're really sick, patients tend to take a common physiological pathway of multiple organ failure. But having said that, it is of course important to be able to stratify between patients, because you are spot on with your comments there. So typically ICUs in the Netherlands and I would say the most of Europe are not organized like you suggest by specialty such as cardiac care ICU or neuro ICU. So we have a mixed ICU. However, the admission types are recorded for both for administrative purposes, but also basically just because they are in the routinely collected patient data. So, for example, we have broad categories such as surgical admissions, medical admissions, but also have narrowed that down to reason for admission, such as following cardiac surgery, neurosurgery, or after sepsis or after cardiac arrest. So they're pretty well labeled. So data scientists would be able to easily stratify these patients for the use of their analysis.
That's really cool. So and I think that's one thing that's always worth keeping in mind when you're trying to view data sets that are as comprehensive as the one that you've created, that essentially when you are looking at these patients, they are all co-located within the same ward. and you can stratify via the data, but essentially we aren't looking at sort of geographically different patients, as in they're located in different segments of the hospital, which would be the case for other data sets. For example, I believe in more like in the UK and the US, where these patients are stratified and I guess sequestered according to clinical classification. So that's really interesting. So one of the things I want to talk about, because as a clinician, you are at the interface between patients and their healthcare outcomes and patients in their experience. You have essentially a front row view. Actually, you're not even in the row. You're up on stage as the clinician with these patients having their clinical outcomes. And I'm a bit curious about, from your clinical perspective, given that there is a burden here that you need to be making sure that the data will be of benefit to the patients and also not of risk to patients, for example, de-anonymizing them, displaying data that could be used to identify them in some way, and also just sort of preserving the dignity of the patient whose data we are using, regardless of what their personal outcome is. Because, what's data to a data scientist is actually, a human being. It's themselves to the patient. It's another person's family member's outcome. And I'm a bit curious about this, and this is just going to be a broad question. What are sort of the priorities that you have from an ethical perspective, beyond the obvious things like de-anonymization, that you look for to make sure that this data will be of benefit to a clinical population and is therefore worth the burden?
Yeah, well, so it's probably important to first point out that the release of AmsterdamUMCdb is actually part of a broader initiative by the European Society of Intensive Care Medicine. The society has put forward a mission called the Data Sharing Initiative. The reason being that up until very recently, there was only freely intensive care patient data available from the US. And that means that these patients and the models that are being created for them do not necessarily, or actually most likely do not, transfer easily to, across the pond, so to say. So that brought us to a challenge that you alluded to, because in Europe, the privacy laws, and the main one is called the GDPR, so the General Data Protection Regulation. It's a European wide regulation that is considered law in all of the countries in the European Union. So, but this law is a bit stricter than the US privacy laws, which are often referred to as HIPAA. So that means that we, by definition, had a large challenge related to the de-identification strategy that we took, because the simple removal of identifiable objects is not enough for this regulation. And also from a clinical perspective, I think it is actually debatable whether that is enough. So as you said earlier, and I fully agree with this, I mean, when you look at the data as a data scientist, you might not always recognize that underneath this data is a real patient that has probably suffered, may have died, and has basically donated their data through us for the benefit of future patients. And it is very important to remember that even though these data has been thoroughly de-identified to comply with the law, it is still very much needed to be aware of the fact that you need to treat this data with the dignity that comes with treating patients. Does that answer your question partly, or do you want to discuss a different topic?
I think that's a very good beginning to the question. As a clinician, what would you consider to be a good return for the patient population for having donated their data, so to say? Where is it just, if we can objectively create algorithms that provide a measurable benefit to future patients, that is I guess, sufficient and worthy of the burden of collecting this current data? Is that just a good, is that sufficient? Or as a clinician, do you think it needs to go beyond that in some way in order to make it worthwhile for the patients who are currently going under the burden of monitoring and extra collection?
Yeah, so it is a difficult question to answer because it comes with a lot of cultural perspective, I would say. So in Europe, healthcare is mostly based on the principles of solidarity. Most countries have almost 100% coverage of health insurance, and in some countries it's even the public hospitals are free to the public. So that means that in Europe there is a strong notion, if you will, to also be kind of wanting to help by donating your data. So this is this should be some basis of viewing how patients and doctors deal with this, and this is exactly why we want to make this data, well, basically freely available. Of course, you need to fill out some forms to access the data, but basically anyone in the world can use it, because we feel that this data should especially not be only available to those who are able to pay for it. For example, the large tech companies or conglomerates of pharmaceutical companies. I'm not saying that they should not have access to the data, because I think they can also benefit future patients, but it is very important that these data are also accessible to the public domain. And by the public domain, I mean healthcare institutions, universities, data scientists. Now, Mimic has been very, very popular, so I think almost 10,000 people would have access, would now have access, and I think many hundreds of models have been built. So I expect that this Amsterdam UMC database will follow suit, and hopefully also the other initiatives promoted by the European Society of Intensive Care Medicine to also share their data. I'm not expecting that all these models will make it to the bedside, but as my research group locally specializes in actually bringing models to the bedside by integrating them into the electronic health records, it can be a great way of using basically what we're doing is crowdsourcing the opportunity to help here and use the wisdom of the world and those that want to help improve the care of critically ill patients. We're basically using this knowledge to then test that hopefully soon locally to use these models for real patients we are seeing now.
That's really interesting, and it actually segues into the next sort of section that I wanted to discuss, which was the algorithms for clinical decision making. Now, of course, every data scientist has like 20 algorithms, that they're rare and ready to go, that they've tested out, and things like that. But I think one of the things while we have a clinician at hand to answer these questions, I'm curious from your perspective, sort of what clinical settings and sort of what physiological mechanisms do you think are most apt for data analysis and predictive algorithms and things like that? Because you can always try to create an algorithm that tries to map inputs A onto outcome B, but the fact is there are a smaller subset of them that are actually providing information that a clinician can use to actually improve the patient's outcome. And so this is a very broad question, but what are certain aspects of it that, for example, that are easily interpretable or actionable by a clinician? What are the areas that you think are quite useful to say, here's where an algorithm can really help us make hard choices based on the clinical science and not just the data?
Yeah, so this is of course the holy grail of predictive analytics and personalized medicine you're talking about. So reflecting on that, I would first like to comment that it is really problematic that there are so many models being built that do not make it to the bedside. So if you look at the technology readiness levels introduced by NASA originally for their space missions. It's usually a 9-point scale where 9 means that it is actively clinically used at the bedside. But most models only reside at level 3, 4, 5 maximum. So that is a problem, and the reason why that is, and this is exactly what we're trying to address by releasing AmsterdamUMCdb, is that data scientists and clinicians don't generally know each other that well. So they tend to not talk enough to each other. So that is why we have posed a number of rules to gain access. And the most important one of this is that data scientists need to co-sign the access form with an intensivist. So they will actually start talking to each other. So having said that, there are two major categories that clinicians would like to use models for. One is related to the organization of intensive care units. So that would relate to predictions of how many patients we can expect to be admitted to intensive care within a certain time frame, or whether or not they would be expected to be readmitted soon after they would have been discharged. So I would group them under the term organizational, and the other ones are more clinical. And to give you an example that we have been actively pursuing, and it's currently live at the bedside. So we are predicting for every individual patient the exact amount of antibiotic that he or she might need at a given time, instead of using standard dosing. And we're currently testing that in a randomized controlled clinical trial. But you can also think of things like can or cannot not remove the mechanical ventilation tube in this patient. Will this patient develop a heart rhythm disturbance such as atrial fibrillation in the next 6 hours? Is the lab value that is higher than expected here, is that something I should really worry about, or can I just ignore it? Or will this patient become more infectious over the next 6 hours? It is very important there that the clinician should be able to see that these predictions are actionable. And because it doesn't really help you that much if you are presented with a prediction that you feel you cannot really do anything about. It is therefore also quite helpful if the models are at least partly explainable. So it gives clinicians a little more trust in the model that is at hand. Although not, I mean, most people say this, but I think it's a little exaggerated. So it's not really a condition that is an absolute requirement, because if clinicians will see that the model is usually right, they don't tend to really mind that they don't fully understand what is going on in the black box, because if you look at it, most clinicians can be considered a black box too, right? So you would need to also trust your other consultants on some opinions they have. But having said that, actionability and explainability are, of course, very important there.
Yeah, that is really interesting, especially because an algorithm, even if it's not perfectly right, if it sort of is capable of spurring further clinical investigation. So, for example, if a clinician doesn't entirely understand why an algorithm has come to its exact decision, there's nothing that prevents a clinician to look at the components of this or the patient's information and try to start understand and detective out or sort of piece together what is actually wrong with the patient. So the algorithm, doesn't need to be necessarily doing the decision work of the clinician. It can just be helping the clinician direct their focus to figure out why a certain patient is abnormal. It can be, the beginning of that clinical investigation, not the end decision by itself.
Sure, yeah. So I agree fully there. So it is important that of course that these models are safe. So they need to be tested well before use. There's also a European regulation related to that called the Medical Device Regulation. So that means that it is becoming harder and harder for clinicians and research groups to bring a model to the bedside at times when it is most needed. But that is also for a reason. So you want to be sure that that the models don't produce advice that is obviously wrong. On the other hand, so I believe in a thing that is popular now called hybrid intelligence. So trying to combine the intelligence provided by predictive models with that of clinicians. So as long as there is a so-called air gap between the prediction and the actual action following it, and as long as there is a clinician in between, I think the world can only get better by trying to explore how that might improve the health of future patients. And I have also noticed, because we have two models live in our clinic, that that the fear that clinicians means some data scientists fear that clinicians might not use their models or predictions because they may feel they don't understand it, or they have the feeling that they might be replaced. But that is not my experience at all. I mean, doctors really love it because they just acknowledge that medicine is very hard. They have their specific expertise and also a lot of experience depending on the seniority. So they do bring in a great level of professionalism that is needed, but they are very ready to acknowledge that it's just impossible to oversee the large data streams that come towards them from all our monitors and devices minute by minute or even second by second. So it is very helpful to have a computer help you with that.
Yeah, I think that's one of the things that can never be understated about a computer operating in something like the critical care ward, where these data streams are continuous. They're very high density. They're very high frequency. There are a multitude of modalities or you can consider them data streams that each individual patient is creating. And a clinician can only be in so many places at once, whereas a computer, as frankly stupid as computers can be, they have nothing better to do than just sit there and just stare at the data. I sort of compare them to they're like spiders in a web. They have nothing better to do than just sort of sit there in that web and wait for a fly to come and shake the web and act on that. Whereas, human beings, they wear out, they get tired, they need to be many places. So that specific aspect of algorithmic intelligence, just the perseverance and continuity, is something that shouldn't be underestimated as a strength somewhat unique to computers.
No, exactly. So and not only they are just there sitting and waiting for things to happen, they also have nowadays the capability, and humans don't, to consider all data points that are being thrown at them. Whereas human beings, they can. I mean, it's just physically impossible to understand the magnitudes and the hidden signals from these data streams.
Yeah, I think that brings up a really important point where the computers have a unique aspect just due to their increased computation and ability to focus through that computation, that they can essentially consider different components and conditionalities that human beings can't, where it's very easy for computers to say, well, let's look at this data stream, condition it on this one, and provide some type of complex inference. And then they can flip it around and compare data stream 2 back on data stream 1, and they can do all these different comparisons very quickly and continuously, whereas a human being essentially sort of needs to take sparse elements of the data and only consider them more or less individually. And, when a clinician can put multiple data components together on, well-known physiological mechanisms, but, when you're trying to have it be continuous and through maybe mechanisms that a clinician doesn't consider as much, that's where computer can come in. One of the challenges I think that algorithms have, and I was curious about this because you've created this very dense multimodal data set across a large number of patients. And when we're trying to create algorithms, typically what we do is, in a clinical settings, modalities drop off, sensors drop off, they become dirty, they become corrupted, or they can, they can be sensitive to noise. And so I think one of the interesting challenges of transitioning from an algorithm that works in a research paper to an algorithm that reaches that technological readiness level 9 is that what you do when the data deviates from what you expect. So for example, say you have a patient with a bedside monitor and you're getting heart rate, respiratory rate, blood oxygen saturation, blood pressure, and you've created this algorithm that seems to be useful for detecting cardiac arrest or something like that. But then when that patient loses, a heart rate node, or their PPG comes off their finger and things like that, where the data starts getting corrupted, the algorithm that you trained then immediately starts losing data. It's not well adapted to that. It's not ready to be losing data at random and things like that. What are good ways, as a clinician, you think that people can be sort of creating scenarios where you can test this and say, okay, we know that these are typical ways that the data fail, and this is how we prepare and double check that our algorithm still works?
Yeah. So excellent question, Glenn. So let me try and answer in multiple dimensions. So first of all, you need to be sure that the data is at least valid to some extent to create a model, right? So even in AmsterdamUMCdb, there are probably many data elements that are noisy. And of course, I don't know by heart which ones they are. Although the good thing is that many of these data points have also been validated by humans, just by documenting this in the electronic health records. Nurses and doctors have done this at least every hour, but the minute-by-minute values, they can be off. Of course, there are data cleaning techniques to detect outliers, and you can use combinations of events, a combination of signals to make sure your data is reliable, but it is always a risk. And the same is true, of course, for when you have developed a model and you're going to test it in the clinic, that you might risk a lack of features, so to say. So one feature may not be available that is critically important to the model. Now, of course, first of all, you want to avoid it as a model maker or a model developer. And in fact, the absence of a data point can also be a feature in itself, right? So that is one creative way to deal with that option. But also it is always good to verify signals such as, for example, heart rates. So this usually comes from multiple sources here. So you have your arterial line, your plethysmogram, your EKG, and sometimes even more of those. So you can probably do a check in your real-time data stream whether or not a data point is actually reliable or is it really missing. But the most important thing then, I would say that these are basically all non-problems, because now we do not have a model, and then we have a model that might assist the clinician in a very good way or in a slightly worse way, but still much better than having no computer giving an advice. So my motto is it's always better to have a model than no model.
And I guess adding on to that, there's nothing stopping an algorithm from quantifying its own uncertainty and quantifying its own predictive quality. So it's not, say, different sensors start dropping out, and your algorithm is heavily dependent on sort of the joint distribution of those different values, that there's nothing stopping you from just saying, look, the algorithm's still running and calculating something, but like 3 out of the 5 of our best predictors have now dropped out, and the correlations between those are now lost. So maybe just stay tuned until this is back online, and add an extra grain of salt to this prediction right now.
Well, so I totally agree. So it's essential that these estimates of uncertainty are built in. It's so logical that I would not even consider this to be a feature of a model. It would just be a necessity. And to add to that, I mean, so given the fact that by definition, this may be a philosophical discussion, it is virtually impossible to prove causality with whatever model and respective data. It is very important to actually test these models prospectively in a randomized controlled trial, and with assessment of outcomes that are relevant to patients rather than doctors. So I would say that would be the ultimate proof of whether or not that it would be a problem that sometimes data points are missing, or maybe that would not be a significant problem at all.
On the issue of making sure that your algorithms ultimately result in some type of metric that's most important to the patients, what are some things that are, as a clinician, what are some things that maybe data scientists are likely to miss, where, you know, we'll focus on things like ROC or predictive probability and things like that, or, you know, predictive accuracy. But if it doesn't relate exactly to the actual clinical outcome of interest, then essentially we're optimizing algorithms with respect to the wrong metric. What are some of the ways that, you know, we can make sure, what are some of the things that are important to clinicians or patients with regard to metrics?
Yeah, so for patients, the most important thing, and I mean, data scientists can allude to that, is to be healthy, right? So mortality is, of course, a very important endpoint, because almost every patient wants to survive. But if that survival comes with a significant amount of disability, it may sometimes not be worth the treatment. And so what patients care about is, can they lead a healthy life after being critically ill? So the ultimate outcome is likely always something like quality adjusted life years or similar, right? And this can have many aspects. Now, the problem is that data is not usually available to data scientists. And in fact, those data is also not available in AmsterdamUMCdb. So this is not a bad thing per se, because we can, of course, model towards other outcomes that I would call surrogate outcomes. And even mortality can actually be considered a surrogate outcome in that way, even though it is a very important and hard endpoint. But you could also, for example, relate your outcomes more to functional skills such as Glasgow Coma outcome scores or scales, or absence of presence of ventilator-free days, or delirium-free days, or days on vasopressors. But they become gradually less important to patients. They can be very important to avoid, because it's physiologically natural that if you prevent that, your chances of having more quality adjusted life days or years is also greater, right? Because you first need to survive in order to have a quality of life. So it is good to model against these, but then these should always then be tested in real life, whether or not they are actionable. So they will actually produce the effect they are built for. So for example, if you model for mortality and have an actionable model, you first want to show that that model will actually help reduce mortality in clinical practice in a randomized controlled clinical trial. And then from those patients, you of course need to investigate whether that also leads to a life they want to have, and quantify that. and that is a long way, right? So it is okay to have intermediate steps in between, but that would be the ultimate goal, of course.
And now we've almost used up all of the time that we have with you today. But one last thing that you mentioned that I think was really interesting was the issue of ultimately these algorithms need to be tested in, you've said, a randomized control trial. But I'm also curious because, obviously the RTC is generally at the end. Well, not actually at the end because, you can always have follow-up surveillance afterwards. But it's sort of that crowning achievement in testing the validity and the efficacy of an algorithm. But leading up to that, there's a large number of other things that you can do. You have that, just the initial research grade comparison, which I consider is probably more akin to a some type of retrospective trial or historical control trial. What are some of those the gradations of convincibility in demonstrating the value of an algorithm? So you've created a paper and the research paper says, yeah, algorithm A compares favorably to algorithm B or compares favorably to do nothing. Where do you sort of step up to there on the way to an RTC?
Well, so first of all, make sure you talk to clinicians, right? And don't just do this once a year. Just do it every day, because you will quickly grasp what they find interesting and what they consider just to be tools for modelers, right? Having said that, so a typical way from a model to proceed to the bedside is, of course, first develop it. And then one of the most important aspects is to use the right outcome metrics. So even if you have a surrogate outcome, or let's take an in-between outcome, such as ICU length of stay, or for example readmission rates, you have to understand that these events are usually imbalanced in a population, right? So that also implies that the area under the receiving operating characteristic is usually not representative of the true performance of a model. So you would rather resort to the area under the precision recall curve for events that are more rare. So you see that a lot that people will only report a metric that they're used to, while this does not necessarily mean that their model is good. So then the next step would obviously well, of course you would have your training, testing, validation on a data set, but it is very important to also test your model on an external data set, which is actually where AmsterdamUMCdb may currently have its greatest value, because there have all kinds of models being developed on many local databases and also some on Mimic, well, many on Mimic. But all these researchers now have a pretty easy way to confirm if their models really hold and are not actually overfitted to their specific situation they've tried to model. So, but then ultimately, to convince clinicians, you would need to take these models to the bedside, and so they would have to become part of a software interfacing with your electronic health record, and then provide an advice to physicians or clinicians, so you will, in terms of actionability, because it is nice to show clinicians that you can predict well, but like I said previously, it is ultimately important that clinicians can see the value for their patients, so for the one patient they have currently in front of them, because otherwise it's just like reading a trial that pertains to many patients, whereas it is of course the individual patient that matters most to the individual clinician. So to convince them, you need to move from bites to bedside.
Well, Paul, thanks so much for spending some time with us today to discuss this. Honestly, you've brought up about as many more interesting questions or more than we've even covered today, but this has been really interesting. It's always nice to hear a clinical perspective on this, and especially a clinician such as yourself who's familiar not just with the clinical application and the bedside operations, but also the algorithms and understanding what the priorities of this algorithmic development needs to be, because that is really helping making sure that we are heading in the right direction for quantitative sciences to actually be helping patients in the long term. With regards to your data set, obviously this is a tremendous thing for patients down the line, but it's also tremendous. You've done a tremendous thing for the healthcare profession, for data scientists, for clinicians to start having more of that interface. And obviously just as sheer productivity of your work, this is pretty big. So again, thank you both to you and what your team has done, because it's obviously a very big team that's needed to do something this good.
Yeah, thank you so much, Glenn. And can I just ask you maybe to point your readers to or your audience to AmsterdamMedicalDataScience.nl, because basically we're inviting everyone to play with this data. And when I say play, I don't mean play like a data scientist, but treat the data like a doctor and help future patients. So that would be great.
Yes, I can actually personally confirm that the website is very interesting. It has a variety of very interesting links. Also check out Paul Elbers' group research page. It also has a lot of interesting information on it, interesting links. This is part of a community that, as Paul mentioned at the beginning, that there are these, these digital health initiatives at work. There's a community there. It's a scientific community, but also, very much a data-driven community. And they're doing a lot of interesting work, and a lot of the stuff just even makes for a good read. So definitely check it out. We have we're popping up the link in the description below, and I'll try to pop it up on the page as well. So Paul, thanks so much for your time today. I really appreciate it.
Thank you so much, Glenn. Great talking to you.
Bye.
Well, that's it for this episode of the Pod of Asclepius. We hope you enjoyed it and will tune in for our next episode. If you're watching from YouTube, don't forget to subscribe to our channel and leave a like. You can also follow us on our other social media channels, including LinkedIn, Twitter, and Instagram. Have a great story or presentation that's ready for prime time? Or know someone who does? Drop Glenn an email because he'd be happy to hear from you. We would like to thank our sponsors from the American Statistical Association section on Statistical Learning and Data Science, section on Medical Devices and Diagnostics, and North Carolina chapter. The views expressed on the show are those of the speaker and not their employers, our sponsors, or anyone else not saying the words.